Welcome to the discussion on fretting corrosion. This is a special type of you can call it corrosion occurring when the structures are loaded heavily and the interface between the mating parts, the structures are not supposed to be moving against each other. So, in the structural design what you do is for example, you say riveting, right. Riveting is a mechanical joint. Similarly, you can talk about bolting, or you could see a tie plate that you see in the rails, right, been grubbing the rail with the wooden or the concrete slabs. Now, these are essentially the structures which are joined by a load, okay. But it is easier said than done, right. When you apply when you have a bolt, for example, a bolted structure, there can be a vibration. When vibration occurs, the interface they start moving, at certain distance. It could be as low as an angstrom, a nanometer distance. So, there is a relative movement of the interface which are heavily loaded, which are not meant for moving, they are supposed to be held tight. In that case, there is a rubbing action, there is, you can call a wear if you want to call, okay. But in this case, we call it as fretting damage, because in the wear process, the movement between the mating surfaces are quite large, right. Let us say in the ball bearing, within the race, you have the balls, they start moving, okay, it starts moving, maybe a few meters, they start moving. The gearbox, gear starts, moving, that is a damage, but that we call as a wear process. But a bolted interface, because of vibration, it moves, it giggles, right. That movement is very small, and when it moves and we also have exposure to the air or a corrosive environment, that damage we call them as a fretting damage. So, the fretting damage, the fretting corrosion refers to loaded interface, first of all, which are not supposed to move against each other, and they are exposed to air. air is a corrosive medium here, there is an oxygen present, okay, and then they start vibrating. And the distance of vibration, the distance of movement I would say, is of the order of 10 power minus 8 centimeters, is close to an angstrom, imagine. When these things happen, interface suffer damage called as fretting damage, fretting corrosion you call it. Now, how does it look like, okay? Appearance. It appears as pits, appears as grooves, okay, and covered with corrosion products. Now the fretting, damage and fretting corrosion is also called as, friction oxidation, called also as wear oxidation. We call as false brinelling, okay, and maybe called as chaffing. Now look at this, the term brinelling is arising out of the fact, the Brinell hardness, Brinell indenter, right? When you carry out a hardness test using a Brinell indenter, you see kind of what, hemispherical shape, right? Brinell is spherical balls, right? So the appearance of that indent is very similar to the fretting damaged locations, the pits that you talk about. So that is why they call as a false brinelling. It is arising out of the appearance that you see that. The friction oxidation and wear oxidation, we will see later that it is more related to the mechanistic aspect of fretting damage, how the fretting damage occurs in reality actually. Now the importance of that, it is very important for engineering structures. Okay. It can be in aerospace industries, transportation industries, it can happen in a in automobile for example, it happens in rails, it could happen in a heat exchanger where you are securing with bolts and then when the liquid pumps, it pounds the thing, then start vibration can take place. So it happens in several engineering structures, it can happen. It can also happen in bio implants. that you do for orthopedic applications, right? You do that. I give some examples to get a feel for the fretting damage that can happen in engineering structures and as well as in the bioplants. Okay, the one of the classic case of defining the fretting damage is press fitted ball bearing race onto a shaft, right. Isn't it? Suppose you have a shaft, for example, you may have a shaft here, and right. This is the uh, sectional view of a bearing, right. This is the ball and this is the race, right. This whole thing is called a race, and this is press fitted, right. So when this shaft rotates, what happens? The race, the ball starts, starts moving, right. The whole race starts moving actually around the balls, right. Of course, balls are located, it's not going to move from the place, but the race is going to move. But this press fitted place, this is supposed to be intact, it's not supposed to be loosened at all, but in practice it would happen. Okay. However well that you fit it, depending upon the loading conditions over a time period, you see that there is going to be vibration and relative movement. And the failure that occurs here within this interface we call as fretting corrosion. The failure that happens here, what do you call this? We call a wear failure. If there are some corrosive liquid here, so happens, then it becomes a corrosive wear. So the difference between this and this place is that the movement, relative movement between these two are not very large, but here the relative movement is quite large. The other example, clear example that one can also look at is the axles of an automobile. Assume that I have a small car, it is manufactured at one of the automobile company, and they transport these cars from one place to other place before it is being sold to showrooms, for example. How do they transport? They transport through trucks, right? They transport through the trucks. When they transport through the trucks, the axle does not rotate completely, rather what happens now, it jiggles, it just starts vibrating back and forth. On the other hand, when you drive the same car, the axle undergoes complete rotation. The failure that happens during the second one is called wear failure. The failure that happens during the first one is called as fretting damage. So, the difference is that the relative moment of this happens. In fact, one of the real problems, which is in fact a burning problem, that happens for the steel industries, and I do not know how many of you have seen some of these trucks carrying coils, hot rolled coil, cold rolled coils, they have been wounded and kept on the truck, right, they are rounded ones, I have seen there are a few tons. These coils sometimes are used for automobile companies, they are thin sheets, right, they are coiled and they are transported from the steel company to automobile company or any user companies. What happens when the truck moves, the whole coil, you can see that they start vibrating, there is just something like bumping, you can see that. The load is few tons, not simply very low load, there are few, very high loads. So, when there are high loads between this sheets, the coil interfaces, you will see a clear damage, and that damage is nothing but a fretting damage. You will see all pits, like a biting pits, you see the things, and in fact this is one of the perennial problem for the steel manufacturers. Okay. So, in essence, to say that whenever we have a loaded interfaces, very heavily loaded interfaces, and they are under vibration causing a relative movement between the interfaces, and you have exposed to the corrosive environment like air, they are going to cause a premature failure, the damage, and such a damage is called as fretting damage. Now, I just give an example how this can happen in an implant. In a body plant, you suppose you have broken leg or something, so it is for, let us say, a long bone, and you have a support of of a, let us say, stainless steel rod. Supports on the leg, for example, and you start walking now. Okay, what happens now is going to rub. There is going to be rubbing between the bone and the metal implant. When it happens, then the bone wears out. Then what happens? Now you see that now then there is going to be fretting damage on the metal. Please notice that the fretting damage is not just confined to only metallic structures. It can happen on ceramics. Suppose I have two ceramic interfaces, right? It can happen. Very interestingly, people have noticed fretting damage even on the noble metals. Okay. So, that means it looks that the corrosion is not the main requirement for fretting damage, though corrosion assists the fretting damage, but corrosion is not really a requirement, basically because we talk about noble metals suffering the fretting damage, ceramics suffering the fretting damage. So, it is just not combined only to the metals, it can also happen to the non-metals as well actually. So, there are 3 basic requirements, okay, for the basic requirements are the interface must be loaded, there has to be vibration or repeated, okay, relative motion, between contacting surfaces. Okay. Third, the load and the movement are sufficient enough to cause slip, right. So, it is a mechanical damage that taking place. The contact surfaces, you know, when the surfaces are rubbing, for example, okay, what really happens, you know, when they are rubbing, it leads to seizing, just sticks, you know, when you start moving fast, you can stick and then move, right, it is called seizing. You can also have galling. You know what the galling means? When they stick, and when you remove it, it just comes off from the surface, right. It just comes off from surfaces. It happens in the soft material, the soft material. For example, you have a zinc, and you know, zinc zinc bolts, for example, fasteners. You apply a coating. You have with the threads. You suppose you just screw them, and what happens? The zinc will stick and just come out. Okay. So the galling comes when we have softer material, when they stick, and then when they move further, apply the load, it just comes off. Okay. So the fretting damage leads to seizing and as well as the galling, and then finally what happens? So they are all related to materials removal from the surface. So we have now so far described what is mean by fretting damage and where it occurs, what are the requirements for a fretting damage, right. If you need to control fretting damage, so we need to discuss. In the mechanism, there are 2 types of mechanisms, okay. One is called as wear oxidation. The other mechanism is oxidative wear. You will see why we are proposing the mechanism. What do you mean by mechanism? So, how are the processes are taking place? How are the physical processes are occurring, right? What are the steps involved? Okay, what are the route in which things are taking place? So, it talks about the path. Now, how do you in many cases find out the path? You may have to analyze, suppose there is a process, you might analyze after the end of the process and then try to build a theory, an assumption to describe the starting point, end point, and then see how things have happened, right. When you do that, then of course you can also do a controlled experiments and to prove that the path that you describe is right or not. So essentially you need to look at the experimental evidences to support this. Theoretically you can do another part of it actually. Experimentally you need to have a data to support the mechanism. In this case, when you have a metallic surface, the end product is always an oxide particle. You can create an oxide particles by two means. One, I start with the virgin metal, right, nicely, and because of rubbing action you get a very fine particles, powders of the metal. Because they are very fine, when exposed to the atmosphere, they turn into oxides. One theory, look at it. The other theory is that what? Oh, look, most of the metals they are covered with oxide layer, right. What really comes in contact with surface is not really metal, pure metal. So, when you have a contact surfaces, when you apply a load, these oxides fragment and become powders, because your end of the experiment you see what on the surface oxides. So, two possible routes are possible, okay. So that is how it means that wear oxidation mechanism and oxidative wear mechanism, both are successfully explaining the experimental observations, right. So, that is what happens. So, you want to do that schematically, you can do this, you can say that okay I have, so the first is the wear oxidation mechanism. So, you have the contacting surfaces, the contacting surfaces are not atomically smooth, right, they are not atomically smooth. So, how do they do? You always have hills and valleys, right. So, you have always asperities, right, this you have hills and valleys, something like that. So, I can just discuss this and I can draw schematically something like this. So, they are under load, am I right? These are under load. When they are under load, you have oxide free metallic surface. What happens? It leads to cold welding. They weld each other. Some kind of local fusion takes place between these two surfaces. And you apply a load, a shear load onto this. Now what happens? Because you do not need too much of load in order to fragment this asperities, contact points, right. So what happens now? You will see that course new things have come and it creates of course a newer surface, and you have fragmented particles on this actually, right. These are, what are these? These are fragmented metallic particles. When we have very fine fragmented particles and surface is very reactive, so they get a what? They get a, all they get oxidized. This is the one mechanism, okay. The other mechanism is what? Is oxidative wear. It assumes oxide film. Coverage, and it rightly so, right. Most of the engineering materials, engineering alloys, they are all prone to oxidation at room temperatures, ambient temperatures, and so you can visualize a similar thing. Okay. So these are all oxides, right. These are all oxide films, and the interface is under load of course, and there is a vibration or shear that takes place. So as a consequence, what happens? Now you have oxide particles, okay, and when you generate a oxide particles, fresh surface is created, that surface gets oxidized, and so on and so forth, right. So this process repeats, right. The presence of these oxides or the interface, they damage the surface very severely. Why? Because these are all hard particles and they are the reason for having a pit like appearance, isn't it? They are quite hard particles. And because the relative movement is not too much, what happens? These products accumulate within the interface. See, if it is moving very very far away, it is possible that many of these corrosion products, oxide products are removed from the surface. Because the movement is very confined, these oxide particles remain in the interface and start accumulating the damage with the time. So that is something we should be understanding. So you should be able to have some broad idea about what is wear, what is fretting, and what is fatigue, right. Okay. In fatigue also there is vibration, there is a load, but there is no contact interface, it all happens because of the mechanical deformation, the load, this vibration takes place. Okay. In a wear process, the relative movement is so large, can happen. Okay. Of course, there is a surface damage taking place. In fretting damage, vibration is there, the relative movement is very, very small. That is to be understood actually. So, both these mechanisms, the end product as you see here are similar, and so both the mechanisms are considered to be operating, or it is also possible, it is not just one of the mechanisms, both of them can indeed operate, it is possible in real situations. So, we have seen now the mechanism, then we must know how the fretting damage. It's a very interesting thing. How do you control this? It can be considered as similar to wear process. Can you? Right? So, if it is considered similar to wear process, how do you control wear? Lubrication, right? So, you can apply lubrication, you can do that. What people do, they apply oils, apply low viscous oil. And in order to retain this oil, what people do is they do fast fading. Fast fading makes the surface more rough, and in the surface you put oil, it retains for longer time. Otherwise, in a smooth metal surface you apply oil, this just goes away, right. So, people do a fast fading treatment, and they are also called as Parkerizing, that's the term people use to called Parkerizing treatment. We can do exactly a reverse of this, make the surface too rough. Then what happens? Movement is arrested. Well, you do not have control over movement and all, and you want to choose a material. So, what should be the property of the material? So, hard material, okay. Select hard material. Or what you can do, you can also choose hard and soft material. What does it mean? I can use a gasket, right? I can use a gasket. So, the gasket also arrests the movement of the interface. Okay. So, sometimes people use lead, when you have a lead poured in between the surfaces, what happens? The lead does not allow it to go, but then nowadays lead is being banned, you can't use lead so much because of its toxicity. Okay. You can also do one thing, I can apply a very high load, okay, increase the load. When you increase the load, what happens? The relative movement decreases, right? Increase the load to arrest movement. So, it reduces the slip. If you cannot do that, what do you do? Reduce the load. You do not find any other corrosion mechanism where solutions are given exactly opposite, right. You can see the solutions are exactly opposite, but you do understand what happens, right. So, you can also reduce the load so that, okay, you have vibration, fine, but then when the load is reduced, then the damage becomes less. You can do that, right. If at all not possible to arrest the movement, increase relative movement, right. So, you can also reduce fatigue damage. So, in the lighter vein, if somebody asks a question, any answer give you a mark. Okay. See, they are all born out of the understanding of the phenomena that are happening at the contact surfaces which are loaded. Okay. So, it is a very nice kind of these things, and so that I think we have seen a very, I mean briefly, we have, it is not a, mechanical engineers of course deal with this very extensively. They are in fact a problem for many of the industries.
So the environment is also having an impact, right? So can we?
You can use an, if you use a vacuum conditions, you can do that, but in practice we cannot do that, right. If you can do a hermetically sealed situations, it can happen, but that can hardly possible. But then when you do hermetically sealed conditions, fatigue damage would still occur, right. The rate of the damage would be reduced because the air is not there. So that can be a purely mechanical damage can happen actually, okay. But nonetheless, yes, if you reduce the environmental severity, you could lower the corrosion rate. In fact, the applying this lubrication oil, it has two purposes. One, it lowers the friction. The second, it excludes the surface from the air and other corrosive environment, right. It does both the purposes actually, okay. So, this is one way of isolating the material from the environment. Any other questions?
So can we do this grounding, that is active shaft grounding, can we do this?
Shaft grounding you were talking about in ship, right? Yeah, that is called active shaft grounding. That probably is reduce signatures that happens there, and also to reduce the what you call as stray current corrosion that happens in the shafts, right? Because the current, because it's all cathodically protected, right? So the current will start leaving at one place and entering in another place, right? So the active shaft grounding is to maintain the the path through which the current will flow. It does not go into the electrolyte, it goes through the grounding path. It also reduces the signatures developed because of the continuous rotation taking place. That of course is slightly different subject altogether, happening in the, especially they are required for naval ships. We do not worry too much about what happens in the commercial. Okay, if there are no further questions, I think we shall close the discussion today, and we shall continue our discussion on stress corrosion cracking in the next class. Okay.